Hello, this will be a demonstration of Proposition 9 from Book 10 of Euclid's Elements, which first of all says that the squares on commensurable straight lines are to one another as a square number is to a square number. Now, Proposition 10.9 is a four-part enunciation. There are four things which Euclid proves in this one proposition, so I'll split this video up accordingly. It will be split up into four parts. Each part is dedicated to a different part of the enunciation. So this first part of the video is dedicated to the first part of the enunciation, which tells us that if we have two commensurable straight lines, say A and B, then the squares on these straight lines are to each other are in a ratio of two square numbers. So we want to prove that a squared is to b squared, just as some square number is to some other square number. Now, because a and b are commensurable, we set them out as such, we know that they have a ratio of two numbers. That's what Proposition 10.5 tells us, that any two commensurable magnitudes have a ratio of two numbers. So let's set out two numbers, call them c and d, and let's contrive them such that the line A has to the line B, just as the number C, or has the same ratio that the number C has to the number D. That the line A is to the line B, just as the number C is to the number D. Now, because the line A is to the line B, just as the number C is to the number D, by definition of the number C and D, we can also say that the duplicates of these two ratios will also be the same, so that the duplicate of the ratio which the line A has to the line B is the same as the duplicate of the ratio which the number C has to the number D. Now, the duplicate of the ratio which the line A has to the line B is the same as any ratio of similar polygons put on top of them. That is what the porism of Proposition 6.20 tells us, that similar rectilineal figures are in the duplicate ratio of their corresponding sides. So in this case, let's put some squares on top of these lines. And of course, all squares are similar to one another, so we can apply the porism of Proposition 6.20 to these squares and say that the ratio of these two squares, the ratio of a squared to b squared, is the same as the duplicate of the ratio of their sides, the duplicate of that ratio which the line A has to the line B. Now, we can also say the same of the numbers, that the duplicate of the ratio which the number C has to the number D is the same as that ratio which the number C squared has to the number D squared. This is what we had shown in Proposition 8.11. So the ratio of the square number C squared, the ratio which that has to the square number D squared, is the same as the duplicate of that ratio which the number C has to the number D. Now, we can take these ratios to which the duplicates of our original ratios are the same as and substitute them in. So instead of saying the duplicate of the ratio which the line A has to the line B, we'll say the ratio which A squared has to B squared. And instead of saying the duplicate of that ratio which the number C has to the number D, we'll instead have the number C squared to the number D squared, so that in totality we'll be able to say that A squared is to B squared, just as the number C squared is to the number D squared. This is simple Proposition 5.11. But what we've shown by saying that A squared is to B squared, just as the number C squared is to the number D squared, is that the ratio which A squared has to B squared is the same as a ratio of two square numbers. Of course, the number C squared, that's a square number, and the number D squared, that's also a square number. So the ratio which these two squares, A squared and B squared, have to each other is the same as some ratio of two square numbers. And this is what we set out to prove, that the squares on two commensurable straight lines, A and B, that the ratio of those two squares is the same as some ratio of square numbers. And we've just shown that to be the case, so we have proven what we set out to prove. Now, I can't say QED at this point because the proposition's not over. Again, this is the first of four parts. This is the first of a four-part proposition. So all I've shown is just the first part of this proposition, that the squares on commensurable straight lines are to one another as a square number is to a square number. So an example of that would be say that the line A has to the line B. Because they're commensurable, they'll have a ratio of two square numbers. So let's say that they'll have a ratio of just two numbers. Let's say that the ratio of those two straight lines is the same as that ratio which the number 2 has to the number 3. Well, then what we've shown with this proposition is if we then build the squares on those lines A and B, then the ratio of these two squares will be the same as the ratio of the squares on our numbers. Now 2 squared is 4, and 3 squared is 9. What this proposition tells us, at least what the first part of this proposition tells us, is that the ratio which this square on A has to the square on B will be the same as that ratio which the square number 4 has to the square number 9, which is really helpful. That's awesome. But that is only the first part of this proposition, so I will cut the video here and move on to the second part of proposition 10.9. So now we'll be demonstrating the second part of proposition 9 of book 10 of Euclid's Elements, which says that if a square has to a square the ratio which a square number has to a square number, then the straight lines of those squares are commensurable. So if we have two squares, call them a squared and b squared, like so. And if the ratio which a squared has to b squared is the same as the ratio which some square number has to another square number, so we'll say that if a squared is to b squared, just as the number c squared is to the number d squared, then what we want to prove is that the line A and the line B, those two straight lines, are commensurable with one another. Now, since a squared is to b squared, just as the number c squared is to the number d squared, we were given this fact. And furthermore, the ratio which a squared has to b squared is the duplicate of the ratio which the straight line A has to the straight line B. And furthermore, the ratio which the number c squared has to the number d squared is the duplicate of that ratio which the number c has to the number d. The former we know according to the porism of proposition 620, and the latter of which we know according to proposition 811. We can then substitute these ratios of squares and square numbers for those ratios of which they are the duplicates. So that because a squared is to b squared, just as the number c squared is to the number d squared, we can also say that the duplicate of that ratio which the straight line A has to the straight line B is the same as the duplicate of that ratio which the number C has to the number D. But of course, if the duplicates of two ratios are the same as each other, the ratios of which those are the duplicates are also the same as each other. So that because the duplicate of the ratio which the line A has to the line B is the same as the duplicate of that ratio which the number C has to the number D, we can then say that the line A is to the line B, just as the number C is to the number D. But we remember from proposition 10.6 that if two magnitudes have a ratio of two numbers, they are commensurable with one another. So that because the straight line A is to the straight line B, just as the number C is to the number D, that because the ratio which those two straight lines A and B have to one another is the same as the ratio of two numbers, we can then conclude, according to proposition 10.6, that the straight line A is commensurable with the straight line B, which is what we set out to prove. So we're done with this second part of the proposition. So an example of what we got going on here would just be the converse of what we had going on last time. Of course, the second part of this enunciation is the converse of the first part. So say that the ratio which the square on A has to the square on B is the same as the ratio which 4 has to 9. And of course, 4 and 9 are both square numbers. We can then conclude from this fact that the line A, the straight line A, is commensurable with the straight line B. We can also say more specifically that the ratio which the straight line A has to the straight line B is the same as the ratio of the square roots of these two squares. So because these two squares have a ratio of 4 to 9, we can then say that A is to B just as 2 is to 3, because 2 is the square root of 4 and 3 is the square root of 9. So that's the second part of proposition 10.9 demonstrated. So I'll cut the video here again and move on to the third part of proposition 10.9. Now we will demonstrate the third part of proposition 9 of book 10 of Euclid's Elements, which says that the squares on straight lines which are incommensurable with one another are not to one another as a square number is to a square number. So what we'll have is we'll have two straight lines, A and B, and these two straight lines will be incommensurable with one another. They will have no common measure. And what we want to show about these two straight lines is that the squares on them, constructed like so, approximately like so, that the ratio of these two squares is not the same as any ratio of two square numbers. For if this is the case, then there will be two numbers, C and D, whose squares will have the same ratio as A squared does to B squared. Now, similarly to the second part of this proposition, we can show that if A squared is to B squared, just as the number C squared is to the number D squared, we can conclude from this that the straight lines themselves, A and B, that the ratio which the straight line A has to the straight line B is the same as that ratio which the number C has to the number D. This would just involve taking the ratio of these two squares, A squared and B squared, they're the duplicate of some ratio. The same thing with the ratio of the number C squared to the number D squared, and setting those duplicates, they'll be equal to each other. And of course, the duplicate, if the duplicates of any two ratios are the same, the ratios of which they are the duplicates will likewise be the same. So what we can conclude, if A squared is to B squared, just as some square number, number C squared, is to some other square number, the number D squared, we can say that the straight line A is to the straight line B, just as the number C is to the number D. But if two magnitudes, in this case two straight lines, if two straight lines have a ratio of two numbers, which at this point A and B do, because we've just shown that the straight line A is to the straight line B, just as the number C is to the number D. Because that is the case, we can then say from proposition 10.6, we can then say, according to proposition 10.6, that the straight lines A and B are commensurable with one another because they have a ratio of two numbers. But we were given that the straight lines A and B are incommensurable. So we have at once that the two straight lines A and B are simultaneously incommensurable according to our given, but also commensurable according to our second step. Which then means, because that is an impossible state of affairs, it is impossible that two straight lines both be and not be commensurable at the same time. We can then conclude that the ratio which A squared has to B squared is nowhere equal to a ratio of two square numbers, which is what we set out to prove. So we're done with this third part of proposition 10.9. An example of this would be if we have, say that the ratio which the straight line A has to the straight line B is the same as that ratio which the square root of 2 has to 2. I'm not committing myself to saying that the square root of 2 is a number. According to Euclid, it is not. But for right now, we'll just notate this as such. Say that the straight line A is to the straight line B, just as the square root of 2 is to the number 2. Which then means that the squares on them will have a ratio of 2 to 4. Of course, the square root of 2 squared is 2, just by definition, and 2 squared is 4. And we can confirm that this part of the proposition, the third part of proposition 10.9, is true, because the ratio of these two squares is not a ratio of two square numbers. 4 is a square number, but 2 isn't. But their ratio is of 2 to 4, which is not a ratio of two square numbers. We can confirm that this third part of proposition 10.9 holds. The only thing we have left to do then is to demonstrate the final part of proposition 10.9. So we'll move on to demonstrating that final part of proposition 10.9. Now we will demonstrate the fourth and final part of proposition 9 of book 10 of Euclid's Elements, which says that if a square is to square not as any square number is to any other square number, then the straight lines on which those squares are constructed are incommensurable with one another. So we'll be given two squares, the square on the straight line A and the square on the straight line B. And what we know, what will be given about these two squares on the straight line A and on the straight line B, is that the ratio of A squared to B squared, is not the same as any ratio of two square numbers, from which we would like to conclude that the straight lines A and B themselves are incommensurable. Let's assume that they are commensurable. Let's assume that they are commensurable. Now, if they are commensurable, we can demonstrate in a way similar to the first steps of the first part of proposition 10.9 that if the straight line A is commensurable with the straight line B, then we will be able to show that A squared is to B squared as some square number is to some other square number. This would follow, very briefly, this would follow by showing that because A and B are commensurable straight lines, they'll have a ratio of two numbers, and then we'll show that the ratio of the squares on A and B will be the same as the ratio of those two numbers squared. So that A squared will have to B squared, a ratio which a square number has to a square number. But we were given the fact that that ratio which A squared has to B squared is not the same as any ratio of two square numbers. So that because this ratio of A squared to B squared is both not the same and the same as a ratio of two square numbers, which is obviously impossible and absurd, we can then conclude that the straight lines A and B are incommensurable, which is what we set out to prove. And that is the fourth and final thing we set out to prove in proposition 10.9, and thus having proved it, we are allowed to end the proposition, therefore, etc., QED. A couple things before ending the video. I know it's been a long one, but there's a couple more things to cover with this proposition. The first is that there is a porism appended to it, which isn't really any new information. It's just kind of tying some things together. What it tells us, what this porism to proposition 10.9 tells us, is that straight lines which are commensurable with one another are always commensurable in square too. But straight lines which are commensurable in square are not necessarily commensurable in length also. Reason I wanted to talk about this proposition is just to introduce some new notation. I know I already mentioned in a previous video that this right here will be the symbol for commensurable magnitudes, and upside down will be the symbol for incommensurable magnitudes. We'll have a similar thing going on for commensurable in square and incommensurable in square. For commensurable in square, we'll have the commensurable sign with a line under it. And for the incommensurable in square, we'll have the incommensurable sign also with a line under it. So I wanted to establish that notation before going forward and using it in the future. I also wanted to mention the very final thing about this proposition is that this gives us a very general way of showing which square roots of numbers are rational, not rational in the Euclidean sense, rational in the modern sense, which square roots are rational and irrational. In short, what it tells us is that the square root of some number will only be rational if the number which you're square rooting is itself a square number. If it's not, then it will be irrational. It'll be incommensurable with the unit. That, of course, is a huge contribution to ancient geometry where huge controversies were raised up. For example, once the incommensurability of the diagonal of a square was demonstrated. It was thought that all straight lines were commensurable with one another, just like numbers are, but that's not the case. That's demonstrably not the case. And so after incommensurability was discovered, that was basically the discovery of incommensurability, there was then a long project of showing which lines are incommensurable. So in that case, if you have one square and then you have another square that's double that first one, then the sides of those will be incommensurable. But what if you have a square that's triple that first one, or 5 times that first one, or 17 times that first one? And instead of going through each of those square roots just individually to show that they're incommensurable, Proposition 10.9 gives us a general way to deal with those square roots. It tells us, again, that a square root will only be rational, again, rational in the modern sense, it will only be rational if the number which you're square rooting is itself a square number. But if it's not, then it'll be irrational. So the square root of 4, that's rational. Square root of 9, that's rational. Square root of 100, that's rational, because all of those, 4, 9, and 100, those are all square numbers. But the square root of 3, the square root of 5, the square root of 17, the square root of 80, those will be irrational, or in this case, they'll be incommensurable. Not to say that incommensurability here is the same as irrationality in the modern sense, that's not the case. But it gives us just sort of a modern way to understand this, or at least the modern import of this proposition is that fact, a general way to show which square roots are rational and which ones are irrational, which is, of course, amazing. That's awesome. So that's all I have to say about Proposition 10.9. So I'll end the video here and I'll move on to Proposition 10.10.